Stereochemical aspects of nucleophilic substitution reaction. We are now studying about nucleophilic substitution reaction. We studied nucleophilic substitution reaction follows two mechanism. One is SN2 mechanism, another one is SN1 mechanism. We also studied SN2 reaction proceeds with the inversion of configuration, whereas SN1 reaction proceeds with the retention of configuration. What do you mean by this inversion and retention? Actually, all these are stereochemical aspects, some stereochemical terms. In order to understand these things, we must get some basic idea about the stereochemical aspects such as optical activity, chirality as well as racemization. If you can understand all these things, we can also able to study something about inversion and retention of configuration. All these are some stereochemical terms. Before we start the stereochemical aspects, what do you mean by ordinary light? So, what is the meaning of ordinary light? So, ordinary light means it vibrate all the possible planes surrounded by it. Suppose if we are taking a light source, it having different lot of number of infinite number of planes around the light source. For example, if we consider this as a light source, how many planes are surrounding? This side one plane is surrounding, that side one plane is surrounding, this side one plane is surrounding. So, in all the possible direction it having some planes, all these planes are imaginary planes, it having a plane. So, the light vibrate all these planes. Why we are telling vibrate? Because you know light travels with very high speed. Within that high speed, the light when it emit from one direction, one place to other, it will vibrate. So, it will move like this in the form of wave. That is why we are telling light vibrate. So, light vibrate in some planes. A light source is surrounded by number of planes. If the light vibrate all the possible plane, then that light is called ordinary light. If we are passing an ordinary light through a nickel prism, a prism called nickel prism. If we are passing ordinary light through a nickel prism, ordinary light means it vibrate all the possible planes. That light, when we are passing through a nickel prism, the emergent light, that is the light which is coming out from the nickel prism, vibrate in any one of the plane, vibrate in any one of the possible plane. Such a light is called plane polarized light. The light vibrate all the possible planes surrounding it, it is called ordinary light. When an ordinary light is passed through a nickel prism, the emergent light, that is the light which is coming out from the nickel prism, vibrate in any one of the possible plane, then such light is called plane polarized light. Such a light is called plane polarized light. When we are passing plane polarized light through certain substance, the light rotate. When we are passing plane polarized light through some substance, the light rotate. Then the such substances are called optically active substance. That means the substance which rotate the plane polarized light is known as optically active. Optically active. When we are passing plane polarized light through some other substance, it is not rotating, then that substances are called optically inactive. Based on the concept, that is rotating the plane polarized light, substances are classified into two types, optically active as well as optically inactive. Those substances which have the ability to rotate the plane polarized light is called optically active substance. The angle by which the plane polarized light rotate can be measured by using an instrument called polarimeter. Polarimeter is the instrument used for measuring the angle of rotation of plane polarized substance. There are some substances which rotate the plane polarized light in the clockwise direction. They are called dextrorotatory. There are some other substances which rotate the plane polarized light in the anti-clockwise direction. They are called levorotatory, spelling L-A-E-V-O, levorotatory. Levorotatory means substances which rotate the plane polarized light in the anti-clockwise direction. These levorotatory substances are represented by L substances. Similarly, the dextrorotatory substances are represented by D. Levorotatory substances are represented by minus form. So, dextrorotatory substances are represented by plus form. So, those substances which rotate the plane polarized light in the clockwise direction are called dextrorotatory or D form or plus form. Those substances which rotate the plane polarized light in the anti-clockwise direction are called L isomer or L form, as well as it is also called minus form. There are some isomers which are differ in the direction of rotation of plane polarized light. There are some isomers which are differ in the direction of rotation of plane polarized light. Such isomers are called optical isomers. So, isomers which are differ in the direction of rotation of plane polarized light is known as optical isomers. That means one isomer rotate the plane polarized light in the clockwise direction or right hand side. The other isomer rotate the plane polarized light in the anti-clockwise direction. Such isomers are called optical isomers. Such D and L isomer which rotate the plane polarized light in the opposite direction are called optical isomers, and this phenomenon is called optical isomerism. So, the isomers which are differ in the direction of rotation of plane polarized light is called optical isomers, and the phenomenon is called optical isomerism. If the spatial arrangement of four groups around a central carbon atom is different. For example, if you are having carbon, central carbon, if four different groups are attached to it, the four groups attached to it are different, then that carbon is called asymmetric carbon. The spatial arrangement of four groups around a central carbon is tetrahedral, and if all the four substituents are different, then it is called asymmetric carbon. What do you mean by asymmetric carbon? If the four groups attached to a central carbon is tetrahedral and as well as they are different, then it is called asymmetric carbon. This asymmetric carbon is otherwise called stereocenter. It is otherwise called stereocenter. This stereocenter or asymmetric carbon is the responsible factor for optical activity. So, if a compound contains asymmetric carbon or stereocenter, what do you mean by asymmetric carbon? The four groups attached to it are different as well as they are present in tetrahedral. Then it is called asymmetric carbon. So, asymmetric center or the stereocenter is the responsible factor for optical activity. Those compounds which having asymmetric center or stereocenter having no symmetry. Consider a ball. Place a mirror here. On the mirror you can see the mirror image. Now take this mirror image and place it above the real ball. They coincides with each other. The object and the mirror image, they coincides with each other. Such substances in chemistry, they are said to be, they are superimposable with each other. The substances which are superimposable with their mirror images having molecular symmetry. Take your left hand and place it above the right hand. If you see, they are non-coincides with each other. They are said to be non-superimposable with each other. Objects which are non-superimposable with their mirror images are called chiral molecule. Objects which are non-superimposable with their mirror images are called chiral. This we call it as chiral, or it can also be called chiral, whatever may be. This property is called chirality. This property is called chirality. What do you mean by chirality? The objects which are non-superimposable with their mirror images are called chiral, and this property is called chirality. In organic compound, the asymmetric carbon are called chiral carbon. The asymmetric carbons are called chiral carbon. What do you mean by asymmetric carbon? If the central carbon atom is surrounded by 4 different groups, then it is called asymmetric carbon. The asymmetric carbons are otherwise called chiral carbon. So chirality is the responsible factor for optical activity. Chirality is the responsible factor for optical activity. For example, this is the structure of lactic acid. See the lactic acid, this is the structure. The central carbon atom is surrounded by one side CH3H, COOH and OH, 4 different groups. So this atom is asymmetric carbon, otherwise called chiral carbon. This chiral carbon is normally represented with the star mark. So if you are taking the mirror image, they are non-superimposable with each other. They are non-superimposable with each other. Such isomers are called enantiomers. Such isomers are called enantiomers. Such isomers are called enantiomers. Consider another one example, 2-propanol. The formula for 2-propanol is CH3, CHOH, CH3, 2-propanol. If you draw the structure, carbon, central carbon is there, one side CH3, other side also CH3, HOH. The central carbon atom is not surrounded by 4 different groups, so it is not an asymmetric carbon. If you take the mirror image also, they are superimposable with each other. They are superimposable with each other. Therefore, they are not optically active compound. Object and the mirror image are superimposed with each other, and the central carbon atom is not surrounded by 4 different groups. So it is a symmetric carbon. This symmetric carbon are otherwise called achiral, achiral carbon. Another one example, that is butanol. This is the formula for butanol, CH3, CH2, CHOH, CH3, butanol. If you draw the structure, this is the structure of butanol. One side CH3, CH2 group, another side H, another side CH3OH. That means the 4 different groups are attached to the central carbon atom. So this is a chiral carbon. So the chiral carbon non-superimposable with their mirror image. They are non-superimposable with their mirror image. Such non-superimposable compounds are called optically active and are called enantiomers. Now example 10.8. These are the two given compounds. Among these, we have to find out which one is achiral and which one is chiral. See, this is the central carbon atom. So, tetrahedral is surrounded by 4 different groups. 1, 2, 3, 4. One side H, CH3Br. Here OH. Tetrahedrally, the central carbon atom surrounded by 4 different groups. So, it is a chiral carbon or asymmetric carbon. What about this? This is the central carbon atom tetrahedrally surrounded, but it is not 4 different groups. CH3 is there, H is there, but 2Br is there. So, it is not different group. So, it is a achiral molecule or symmetric molecule. This is asymmetric molecule, it is a asymmetric molecule. Then second example is, this is the second example. Find out the achiral and chiral molecule. This is the question. See this is the central carbon atom tetrahedrally surrounded by one side CH3, another side OH, another side H, another side 1, 2, 3, that is propane. That means central carbon atom surrounded by 4 different groups, so it is a chiral compound. What about this? This is the central carbon. It is surrounded by H one side, another side OH, another side CH2CH3, ethane. This side CH2CH3, ethane. That is similar group. So, it is not a chiral carbon. It is a chiral carbon. So, it is called achiral compound. The third example is, this is the third question. This is the central carbon atom surrounded by one side CH3, other side H, other side CH2CH3, other side Br. Here, this is the central carbon atom, one side H, other side H, Br, propane. So, it is a chiral compound, it is a chiral compound. The spatial arrangement of atom around the asymmetric carbon atom is called configuration. The spatial arrangement of atom around the asymmetric center, we call it as configuration. For example, if you take the configuration of lactic acid, this is the configuration of lactic acid. During a chemical reaction, no bond from an asymmetric center is broken. During a chemical reaction, if there is no bond from asymmetric center is broken, then the product will have the same configuration of the reactant. Both the product and the reactant having same configuration. Then we are telling the reaction proceeds with the retention of configuration. When a chemical reaction having retention of configuration, if there is no broken from the asymmetric center, if no bond from the asymmetric center is broken, then the reaction proceeds with the retention of configuration. If the concentration, if the configuration of the product is entirely different from the configuration of reactant, then the reaction proceeds with the inversion of configuration. We studied SN2 mechanism, there is an inversion of configuration. We studied in SN2 reaction, the configuration of the reactant is completely, totally changed when it converted into product. So, SN2 reaction proceeds with the inversion of configuration. SN2 reaction proceeds with the inversion of configuration. But what about SN1 mechanism? So, SN1 mechanism proceeds with the racemization. SN1 reaction proceeds with the racemization. So, what do you mean by racemization? So, we studied D form, rotate the plane polarized light in the clockwise direction. So, L form or the minus form which rotate the plane polarized light in the anti-clockwise direction. Suppose if you are taking equimolar mixture of both D and L isomer, then the resultant mixture rotate the plane polarized light in which direction? So, of course, which rotate the plane polarized light in no direction. That means the resultant mixture is optically inactive. Such mixture is called racemic mixture. So, racemic mixture means equimolar mixture of D and L isomer. We come to SN1 reaction. So, we studied SN1 reaction. So, the SN1 reaction, example for SN1 reaction is reaction of tertiary butyl chloride with OH minus we study. In the first step, in the presence of polar protic solvent, the reactant get ionized and form a carbocation. This is the carbocation which is going to react with OH minus. When it is react, there are two possibilities. One is the OH may attack the substrate from this side. Another one, the OH may attack this side. Suppose if the OH attack this side, the configuration totally changes. Suppose if OH attach this side, there is no change in the configuration. So, we are getting a mixture of product, one having inversion of configuration, another one is having retention of configuration. The mixture of product, thus for racemic mixture. But what do you mean by racemic mixture? Equimolar mixture of D and L isomer. So, SN1 reaction proceeds with racemization.